We talked a lot about translational motion. We didn't talk much at all, we didn't talk at all about rotational motion. So, over the summer, I'm expecting my AP students to look at these 5 videos, and they'll only be 8 or 10 minutes each. Someone's going to let me know when that gets down there. Yep. They'll only be 8 or 10 minutes long, so you'll be able to use the 5 videos at your discretion. But when you come in back in September, I expect you to have a good handle on rotational motion. Okay, so I got a very active class here, and I've already given them the marching rules. If I say something unclear, or if I contradict myself, which I do a lot, you'll catch me. Or if you need something clarified, let me know if you got questions. On the hill, we love it, don't we?
Yeah.
We left a big part out of the ball on the hill. Let's go over this. On top of this hill, if it's not moving, what kind of energy does it have? Potential energy. And at the bottom it has? Kinetic energy. The potential at the top has to equal the kinetic at the bottom. And what's the algebra? MGH
equals 1/2 mv squared.
Thank you. Do we need to know the mass?
No,
I don't
you
think
just
so.
cross them out.
Doesn't make any difference. But that ball translates down the hill. What else is it doing as it translates?
Losing energy. Getting friction.
Rolling.
Greg, it's turning around, isn't it? It's rotating. What's the difference between rotating and revolving, by the way?
Revolving is on the bob.
Revolving, the axis is outside the bob. In rotating, the axis is
Inside.
And when I say 24 hours, you say rotation. When I say 365, you say revolution. So this is rotating, isn't it?
Yeah.
Because the axis is right there. So up until now, CP and honors, all we've been talking about is MGH equals 1/2 mv squared, which is very misleading. Because at the same time this ball is going down the hill, it is rotating in a clockwise circle, agreed?
Yeah.
That takes energy. That takes energy. And we didn't forget. We've left that whole component out. But now as we get into more advanced AP and even very strongly college engineering, you have to be concerned with that rotation motion. Now, let's look at it in a different way. Let's say we got the ball on the hill, and right next to it we have a flat box. And the box is designed such that it will not roll. It's going to just translate straight down the hill. If they both start at the same time, which do you think is going to get to the bottom first? The sphere that rotates and translates, or the box that just translates?
The box.
The ball.
The ball.
What's going to get to the bottom of the hill first?
Ball.
Let's do the math. They both have what energy? Assuming they're not moving at the top.
Potential.
They both have potential at the top. So the box and the sphere. So the box has MGH joules, and the sphere has MGH joules. At the bottom of the hill, all the MGH of the box gets converted into kinetic. Give me algebra. 1/2 mv squared. That's what we've been doing up until now. But the sphere also has MGH equals 1/2 mv squared, plus it's rotating. Some of that energy has to go into turning the ball around, rotating it down the hill. All right? And I'm going to put something ugly up here, and we'll come back to it.
Wait, the box is just sliding down the hill?
The box is just sliding down the hill, Tara. It's just translating down the hill. Okay? The ball, on the other hand, is doing the same thing, but at the same time it's translating down the hill, what is the ball doing? It's rotating. And that takes energy. That takes energy. So we got this ugly thing here.
Yeah.
For the ball, for the sphere. So all the this potential energy and this potential energy, same number of joules. Let's say 500 joules. All those 500 joules for the box goes into 1/2 mv squared. The 500 joules for the sphere goes into plus 1/2 IW squared. So the energy is split over between the two. So if this is V box and this is V sphere, which number is greater?
The box.
The box. The box will get to the bottom first, which is what you said initially. The box will beat it to the bottom of the hill. Does that make sense?
Yep.
Yes.
Let's look at this. 1/2 IW squared.
What
just W something.
That's what we're going to do right now.
Okay.
1/2,
That's I.
that's I, W squared equals the kinetic energy of rotation. 1/2 mv squared is what? The kinetic energy of translation, which is what we've been doing up till now. Agreed? So, 1/2 we know about. I is inertia. W is angular velocity. Inertia is a very important concept. Inertia, well, let's take a step back. Mass is the resistance to translational motion. If I push this table with a force of 40 newtons, it has a certain acceleration. If I double the mass of the table and push it with the same force, what happens to the acceleration? It gets cut in half. So as the mass increases, the acceleration decreases, it has more resistance to motion. Agreed?
They're inversely related.
They're inversely related. As the mass goes up, the acceleration goes down. Now, for translational motion, the I is a resistance to rotational motion. Okay? And this is a very important concept. The nut who walks across Niagara Falls, what does he take with him?
An umbrella.
Parachute.
His sphere.
What does he take? They always see him.
Inertia.
He's holding a pole.
Oh, no way.
If I put a 2x4 out here and ask you to walk over it, what are you going to do with your arms? You're going to extend them, right? The ice skater who wants to spin very quickly in the Olympics, so she's a blur, or he's a blur, what does she?
And then brings them in.
She brings her arms in to go fast. What does she do to slow down?
Opens them up.
Out here to slow down. Speed up,
Slow down.
slow down.
Yeah.
You walk across Niagara Falls, if you're crazy enough, with a big pole. If you're a little smart, you'd put a brick on either end of that big pole. Because all of it is doing what to the inertia?
Balancing it out.
It's increasing the inertia. So if you increase the inertia, you decrease the tendency to rotate, Tom. You decrease the tendency to rotate. Okay? So the generic equation for inertia is mr squared. Mr squared. Okay.
So you
Thank
plug
you.
that in.
You can plug that in there, but on the next video we'll talk a little bit about moment of inertia, because the algebras are all different for moment of inertia, so we have to be a little bit more careful there. But this is a generic equation. What is it saying? What happens to I as we increase the radius?
It increases.
It increases. That's why the idiot who walks across Niagara Falls takes a big pole with him, because what's happening to his radius?
Gets bigger.
It's increasing, therefore his inertia is...
increasing.
Therefore, his tendency to rotate left or right is decreasing. You're not likely to fall off that 2x4 if your arms are out, because what are you doing to your radius?
Making it bigger.
You're making it bigger. The ice skater, when she wants a big resistance to rotation and wants to slow down, what is she going to do to R?
Make her...
Slow down, increase.
She's going to increase R. She's going to extend her arms. What if she wants to spin very quickly and have very little resistance to rotation?
Small.
She's going to want to bring it closer together. Does that make sense? Okay. So on the next video, we'll pick up right there on the next video when we talk about inertia. Inertia, let's summarize just a little bit. I think I got a minute or a half a minute. Let's summarize a little bit. As a ball rolls down a hill, what type of energy is used up?
Potential.
Potential.
And kinetic.
Potential is converted into two types of kinetic energy. Kinetic energy of translation and kinetic energy of...
Rotation.
But a box doing the same thing only has kinetic energy of translation. She pulls her arms out just like that idiot walking across Niagara Falls. mr squared, she has bigger resistance to rotation. She brings her arms in, less resistance to rotation. Spin slow, spin fast. Spent a lot of time.